Welcome to Blueprint to Reality. Today, we're talking about the challenges engineers face when designing buildings in cold climates. How do ice and snow impact building design, and what solutions do architects and engineers use to keep structures safe and efficient? The weight of snow. One of the biggest concerns in cold climates is the weight of snow. Snow loads can put immense pressure on a building's roof and structure. Engineers must carefully calculate the amount of snow that a roof might have to support, based on local climate data. The steeper the roof, the better it is at shedding snow. That's why you'll often see steep-pitched roofs in areas with heavy snowfall. These designs reduce the risk of snow accumulating and overloading the structure. Ice dams and water damage. Another problem is ice dams. When snow melts on a warm roof and then refreezes at the colder edges, it creates ice dams that can trap water. This trapped water can seep into a building's roof and walls, causing serious damage. Engineers combat this by improving insulation and ventilation in roofs to maintain an even temperature and prevent the formation of ice dams. Proper drainage systems are also key, ensuring that melted snow has a clear path away from the building, preventing both ice buildup and water infiltration. Thermal expansion and contraction. Cold temperatures also lead to the issue of thermal expansion and contraction. Materials like steel and concrete expand in warm weather and contract in the cold. Over time, this constant movement can cause cracks and weaken structures. Engineers account for this by using flexible materials in critical areas, allowing buildings to expand and contract without causing damage. Wind and snow drift. Snow doesn't always fall evenly. Strong winds can cause snow drifts, where snow piles up unevenly on one side of a building. This creates unbalanced loads, which can strain the structure in unexpected ways. Engineers design buildings to handle these uneven forces by reinforcing the most vulnerable areas and incorporating wind barriers to control snow distribution. In regions where ice and snow are common, building design requires careful planning and engineering to prevent damage and ensure safety. From steep roofs to advanced drainage systems, engineers use a variety of techniques to keep buildings strong in the face of winter's challenges. Thanks for tuning in to Blueprint to Reality. If you're interested in more engineering insights, don't forget to subscribe and hit the notification bell for more. Welcome back to Blueprint to Reality. Today, we're taking a closer look at one of the most critical parts of any skyscraper, its foundation. How do these massive buildings, some reaching over 1,000 feet, stay upright without sinking or toppling over? The secret is in the engineering of the foundations. Let's break it down. The basics of foundations. Foundations are essential for distributing the enormous weight of a skyscraper to the ground beneath. But it's not just about supporting weight. Foundations also help skyscrapers resist forces from wind, earthquakes, and even the shifting of the earth itself. There are two primary types of foundations used for skyscrapers: shallow foundations and deep foundations. For small buildings, shallow foundations are usually enough. But skyscrapers? They need something much more robust. Deep foundations explained. Skyscrapers rely on deep foundations, which go far below the surface, to find solid ground or bedrock. The most common types are piles and caissons. Let's start with piles. Piles are long, slender columns made of concrete, steel, or even wood that are driven deep into the earth. These piles either reach bedrock or are driven into dense layers of soil that can support the building's weight. The goal? To transfer the load from the skyscraper down to a stronger, more stable layer of earth. Next, we have caissons. Imagine caissons as giant, concrete pillars, almost like enormous, buried columns that reach bedrock. Workers excavate deep shafts, fill them with concrete, and voila, you've got a super strong foundation. Challenges of building foundations. But it's not always easy. In cities like New York and Chicago, where skyscrapers are everywhere, engineers have to deal with unpredictable soil, water tables, and nearby structures. Sometimes, they use a technique called friction piles, where the friction between the soil and the sides of the piles helps support the weight of the building. Another key challenge is settlement. Settlement happens when the soil under the foundation compacts over time. If one side settles more than the other, the building could tilt or crack. Engineers have to design foundations to minimize this uneven settlement. How foundations resist external forces. Now, skyscrapers aren't just sitting on the ground. They're battling natural forces like wind and earthquakes. This is where the foundation really shines. Wind. The foundation anchors the entire structure, preventing it from swaying too much. Engineers even build in flexibility, allowing the skyscraper to move slightly without causing damage. In earthquake-prone areas, the foundation often has to absorb seismic energy. Engineers use flexible materials and base isolators in the foundation to cushion the impact of an earthquake, reducing the stress on the building itself. Real-world examples. Some of the world's tallest skyscrapers have incredible foundations. Take the Burj Khalifa in Dubai. It stands over 2,700 feet tall and has a foundation that extends over 160 feet into the ground, made up of reinforced concrete piles. Then there's the Shanghai Tower, which uses both piles and caissons to deal with the soft soil and seismic risks of the region. Its foundation is built to withstand high winds and potential earthquakes. So, how do foundations support skyscrapers? By reaching deep into the earth, anchoring the building to solid ground, and resisting the natural forces that could bring it down. Without these marvels of engineering, the towering skylines of cities around the world wouldn't be possible. Thanks for watching Blueprint to Reality. If you enjoyed learning about the engineering secrets of skyscraper foundations, don't forget to like and subscribe. See you in the next video. Welcome back to Blueprint to Reality, where we explore the world of civil engineering and how it shapes our modern lives. Today, we're tackling a significant challenge faced by engineers worldwide: how to build safely and effectively on soft soils. Introduction to the problem. Soft soils like clay, silt, and peat present a huge problem for construction. They lack the strength and stability to support heavy structures, leading to issues like sinking, shifting, and even structural failure. In many parts of the world, particularly in coastal or river regions, soft soils are the norm. So how do engineers overcome these obstacles to build skyscrapers, bridges, and infrastructure on such tricky ground? Key engineering solutions. Over the years, engineers have developed innovative techniques to transform unstable soils into safe building foundations. Let's take a look at some of the most effective methods. First, we have soil compaction. By using heavy machinery, engineers can compress the soft soil, increasing its density and strength. This process minimizes the soil's ability to shift or settle under the weight of a structure. Next, there's soil stabilization, which involves mixing soft soils with stabilizing agents like lime, cement, or even chemicals. These additives react with the soil to improve its strength and reduce its moisture content, making it more suitable for construction. Another technique is deep foundations, where instead of relying on surface soil, engineers drive piles, long columns made of concrete, steel, or wood, deep into the ground until they reach stable soil or bedrock. This allows the structure to transfer its load to a more secure layer, bypassing the soft soil entirely. Finally, there's geotextiles and geogrids. These synthetic materials are laid into the soil to reinforce it, acting like a net to distribute the weight of the structure more evenly. Case study. One famous example of building on soft soil is the construction of the Millennium Tower in San Francisco. Initially built on deep foundations that didn't fully reach bedrock, the tower began to sink and tilt due to the soft soil underneath. Engineers are now using advanced techniques like underpinning and soil stabilization to fix the problem, demonstrating the importance of understanding soil behavior when designing large structures. Building on soft soils is no easy task, but with innovative engineering solutions, we've turned unstable ground into solid foundations for some of the world's most iconic structures. From deep foundations to soil stabilization, civil engineering continues to push the boundaries of what's possible. Thank you for joining us on Blueprint to Reality. If you enjoyed this episode and want to learn more about how engineering solves real-world problems, don't forget to like, subscribe, and hit that notification bell.